Hello and welcome to the notes on 5.3, which is all about the quadratic formula. We'll be talking about the quadratic formula today, as well as something called the discriminant, which is a piece of the quadratic formula. So far we've been solving quadratic equations by factoring and completing the square. But this is really only convenient for some of our quadratic trinomials or quadratic equations. And sometimes factoring and completing the square are really easy, and sometimes they don't do us any favors. So it's important to have a method that'll work for any quadratic equation, and we have that. So while factoring is only convenient for certain kinds of quadratic equations, the quadratic formula works for every type of quadratic equation. All right? So you'll see there the quadratic formula, which is x is equal to negative b plus and minus the square root of b squared minus 4 times a times c divided by 2 times a. And this provides solutions for quadratic equations in standard form. This equation is all about plugging stuff in and spending time really simplifying. So that's where the majority of our work is going to come into today, is just using our order of operations to simplify. You'll notice the spaces between problems here are significant. It's going to take a bit of work, so here we go. Example 1, solve the equation using the quadratic formula. And problem A, 3x squared minus 4x minus 9 is equal to 0. I like to write the standard form of the equation right underneath it. In problem A, these are lined up perfectly. I don't have to move any terms, so I'm all good here. And I'm going to color coordinate A, B, and C just to try to give you a better visual on which one's which. So if you've got a red, blue, and green pen, great. If not, that's fine too. So A is going to be the coefficient of x squared. In this case, that's 3. B is the linear coefficient, so the coefficient in front of x, which in this case is negative 4. And C is the constant, in this case is negative 9. So I have the formula up at the top of the page here, and I'm going to build off of just that one. So I get x is equal to negative b. Now b is already negative 4, so when I take the opposite of it for the formula, I'm going to get positive 4 plus or minus the square root of. Now this is not part of the formula, but I recommend always putting this b in parentheses. So you might want to add that into your formula. It's not part of the original formula, but it's a really good idea to always put this number in parentheses, because you don't want to forget to square the number and the sign with it. Like for example, when I square b, b is negative 4, I need to square the negative 4 altogether. Minus 4 times a is 3, times c, and c is negative 9. All divided by, so one big huge fraction bar, 2 times a. Now this big fraction bar here, fraction bars work as grouping symbols. So it groups the top all together and it groups the bottom all together. So when I'm simplifying, I'm going to simplify the top and simplify the bottom, but I'm not going to simplify the fraction until the very, very end. Okay, so I start working to simplify. When I start simplifying this, I'm going to go through and use my order of operations. Okay, you're really going to simplify under the radical first. So that's my tip. You're really going to focus your efforts here. So underneath the radical, I get negative 4 quantity squared. So I'm going to do exponents first. Negative 4 times negative 4 gives me a positive 16. Then following my order of operations, I'm going to do multiplication. So I've got two parts of multiplication. I have multiplication under the radical, negative 4 times 3 times negative 9. Negative times a negative is going to give me a positive, and then 4 times 3 times 9 gives me 108. It may be helpful for you today to have a calculator out in front of you while we do these notes together. And then on the bottom here, I could multiply that out right now also. 2 times 3 gives me 6. You could do it now or later. Continue simplifying underneath the radical. 16 plus 108 gives me 124. All right. Still simplifying the radical, I need the square root of 124. So maybe we come over to the side of our paper and look at the factor tree. 124 is not a perfect square, so I'm going to look for other numbers that I can pull out of 124. Let's see, well, 2 goes into 124 62 times, and 2 goes into 62 31 times. So I've got 2 times 31, because 31 is prime. Pair of 2's, I bring one out, and I get 2 radical 31. So when I rewrite this, x is equal to 4 plus or minus 2 square root 31 over 6. So far, using a lot of skills that we've already used. And now we're going to go a step further. And this tends to be where students maybe have the hardest part, because this fraction looks so foreign. You've got plus and minuses and radicals and kind of weird stuff going on. So what I'm going to do is, one of the properties of fractions is that I can rewrite this as two parts. So instead of 4 plus or minus 2 radical 31 over 6, I could rewrite this as 4 over 6 plus or minus 2 square root 31 over 6. And I'm going to do that because it makes my reducing of fractions a little bit easier, and this is the way that Savas has their answers written. Now I'm looking to simplify. 4 divided by 6. What goes into 4 and 6? Well, 2. 2 goes into 4 2 times. 2 goes into 6 3 times. Okay, what goes into 2 and 6? When I'm reducing this second fraction, I cannot put a number into the radical, so I'm only looking to simplify. Well, that wasn't very clear. Let's try that again. I'm only looking to simplify the whole numbers. So what goes into 2 and 6? Well, 2 goes in here once, 2 goes in here 3 times. So I'm left with the square root of 31 over 3. This is how your online homework is going to write the answers. I want you to know that this is the same as writing it as one fraction. So since these are both 3's on the bottom, I could also write it like this. And oftentimes a lot of different textbooks or different publishers will. But I just want you to know that these are the same thing. Savas is going to write them separately. It's the same if I were to write them together. Now, this question doesn't ask us to talk about the type of solutions, but I want to do that anyways because that's where our conversation is going today, eventually. So, what kind of number is 2/3 plus square root of 31 over 3? Because I have a square root that I can't simplify out, that means it's irrational. But I don't have any imaginary components, so it's still real. So I'm going to make a note here. These are two real irrational solutions. So it's real because I don't have any imaginary part, and it's rational because I still have a square root. Okay. So let's move on to example B. Okay, so to just copy the same formula from above. For problem B, b squared minus 9x equals negative 27. Now this is not written in standard form. In order for this to be written in standard form, I need ax squared plus bx plus c equals 0. So to solve for 0, I'm going to add 27 to move it over to the other side. And now I have x squared minus 9x plus 27 is equal to 0. From there, I can make a little key with what is a and b and c. A is the coefficient of x squared, which is going to be 1. B is the coefficient of x, which is negative 9. And c is going to be my constant. So I encourage you to pause this, and I want you just to do this first step of plugging in, and then resume and make sure that you plugged everything in the right spots. Okay, so hopefully you already wrote your formula. So when I take the opposite of b, I get 9. And then when I plug in b to square it, I plug in a negative 9. A is 1. C is 27. All divided by 2 times a, which is 1. Okay. Now I'm going to encourage you to pause again. So do little checks for understanding here. Pause this video again and simplify what's underneath the radical. So if you've simplified what's underneath the radical correctly, you should get the square root of negative 27. Okay? And then we're going to have to take the square root of that. So to get caught up here, negative 9 squared is 81. 4 times 1 times 27 gives me minus 108. So I did the exponents and the multiplication in the same step, which is usually what I do. Saves me writing it all out once, if it works for you. And when I subtract 81 minus 108, I get negative 27. So we're here. All right, so on the side, let's worry about square rooting negative 27. Well, back in 5.1, we studied that the square root of negative 27 is the same as the square root of negative 1 times 27. And you should have memorized by now that the square root of negative 1 is I. When I do the factor tree for 27, I get 3 radical 3. Right? I get 3 3s. I need a pair of 3, so I bring one out, and I'm left with the 3 inside. So coming back to my equation, I have 9 plus or minus 3i square root of 3 divided by 2. When I split this up and I rewrite it as 2 fractions, I get 9 halves plus or minus 3i square root of 5 over 2. And then I check, is there anything I could simplify with the 9 and the 2? No. Is there anything I could simplify with the 3 and the 2? No. So that's actually going to be my final answer. Oh, I miswrote that. It's not a 5, that's a 3. Excuse me. I miswrote the number underneath the radical in my haste. It should be a 3. Oops. Before I move on to problem C, I want to talk about what type of solutions does this give me. I know, again, that it doesn't ask, but this is the conversation that we're leading into in example 2, so let's talk about it. Here I have 2. I don't have real solutions because I have an I, so I have 2 complex. And then because I have a square root, I have irrational solutions. Irrational, there we go, solutions. Right? Complex is because of the I, the irrational is because of the radical. All right, first thing we do in problem C is to put it in standard form. So I currently have 6x squared minus 20 is equal to 7x. I need everything to be on one side of the equation. Now, one of the cool things about the quadratic formula is if you decided to move the 6x squared and the minus 20 over to the right-hand side, this would be fine. You could plug it in that way. Everything that would happen is just you would have the opposite signs everywhere, but they would work out so that you get the same exact answer. So I'm going to move the 7x over, but if somebody else decided to move the 6x squared over and the 20 over to the other side, we would still get the same answer, which is kind of cool. So again, right, we need to scaffold this a little bit. We got to work in pieces. I want you to pause this video and just get as far as you can. And if you get stuck on the first step or the fourth step, just resume, and then I'm going to walk you through right now. So pause this and get as far on this problem as you can. Okay, let's see how your problem went. A is going to be 6, B is going to be negative 7, C is going to be negative 20. So when I start plugging in, A is equal to 7 plus or minus the square root of negative 7 squared minus 4 times 6 times negative 20. All divided by 2 times A, which is 6. Okay. And I simplify. So starting underneath the radical, I'm going to start there first. I'm going to do my exponent, so negative 7 squared. It's going to give me a positive 49. And then I'm going to do my multiplication at the same time just to save myself some writing space. So 4 times 6 times 20 gives me 480. And this is a negative times a negative gives me a positive 480. Divided by 2 times 6, which is 12. Whew, this problem has some big numbers. 49 plus 480 is 529. Now, you may start doing the factor tree with 529. You're like, oh, I got to figure that out. And you might give up and get a little stuck here because as you start trying the smaller numbers, you find that there's nothing that goes into 529. And it would really take some perseverance to keep going to figure out that the first number, the smallest number that goes into 529 is 23. And it happens to be that 529 is a perfect square. For me, guys, when I'm doing these problems, I would probably start doing the factor tree. And if I get stuck, like if I get to usually about 7 or 11 and none of those go in, then I probably pause, get out a calculator, take the square root, and see if maybe it's a perfect square anyways. So on this problem, I have this one memorized, but on some of the other ones, like that's definitely what I would do. So that's my tip. If you get stuck and can't figure out the factor tree, punch it in a calculator. All right. So what I have here now is 7 plus or minus the square root of 529, but the square root of 529 is 23. Oh. Well, look at all those integers. I'm going to split this up. 7 minus 23 divided by 2, because this is just a real number. Seven minus 23 is negative 16. Divided by 2 is negative 8. 7 plus 23 is 30. Ooh, hold on. Got an error. This is a 12, not a 2. Boop, boop. Okay, pause. Make that correction. So I get negative 16 divided by 12. I'm going to scroll down a little bit in case this is off your screen. What goes into 16 and 12? 4. 4 goes in here 4 times. 4 goes into here 3 times. So I have negative 4/3 as one of my answers. And then with 30 and 12, let's see what goes into 30 and 12. The biggest thing that goes into there is 6. So 6 goes into here 5 times. 6 goes into here 2 times. So I have these 2 values for my answer. Those are real numbers. Like I could go to a graph and figure out where x is negative 4/3 and x is 5/2. So let's talk about what kind of solutions I have. I have 2 answers. Are these numbers real or imaginary? They're real because I don't have any i's. Are they rational or irrational? Well, they're rational because I don't have any radicals. 2 real rational solutions. Now we know when we're solving quadratics, I could have 2 solutions, 1 solution, or no real solutions, right? Now no real solutions is the same as having 2 complex solutions because those are imaginary. And there's not an example here of 1 real solution, but I'm going to show you that below. Okay. Next idea is what's called the discriminant. The discriminant is like a shortcut to tell us how many solutions and what type they are for a quadratic equation or a quadratic function. So let's say I give you a list of quadratic functions and I'm like, I want to know which ones have two real rational solutions. I don't have to do the entire quadratic formula, which gives me the value of those solutions. I can look at the discriminant to just know what kind of solutions I have. And this becomes really helpful when you're looking at a variety of different quadratic functions and you want to know which ones cross the x-axis. Okay? So the discriminant of a quadratic equation is b squared minus 4 times a times c. Look at this right here, b squared minus 4 times a times c. It should look really familiar. I'm going to scroll up. B squared minus 4ac, b squared minus 4ac. Oh, look at my function right here, my formula, b squared minus 4ac. The discriminant is just what's underneath the radical for the quadratic formula. All right, we call that the radicand. Okay, so I'm going to come back here and I'm going to make a note. This is the radicand of the quadratic formula. And it is completely responsible for the type of solutions that I have. So I've got a table here. In this table, looks at how many solutions are for a function and why the discriminant tells us that. So let's check out this first function here. F of x equals 3x squared minus 4x minus 9. This function that I wrote is the related function for the equation we looked at above. So I'm going to scroll back up to example 1a. 3x squared minus 4x minus 9. 3x squared minus 4x minus 9 equals 0. So here's the equation. Right? I found two real irrational solutions. Here's the related function. All right. So looking at my graph here, this graph crosses the x-axis 2 times, all right? Which means I know that these are real solutions and not complex solutions. Now, when I have two real solutions, they could be rational or they could be irrational. What we saw above was example 1 was irrational because it was left with a radical. Example A. And example C was rational because I had no radical. Okay, so we'll get a little bit into that more below. But here's just an example of the discriminant, b squared minus 4ac. So I plug in b, I plug in a, I plug in c. And when I do that, I get 124, which is what I had underneath the radical in example A. If I have a positive discriminant, if it's a positive number, then I'm going to have two real roots if I'm talking about the function, or two real solutions if I'm talking about the equation. And we'll talk about why they could be rational or irrational for this problem. So a side note, we call it a root for a function, like it is here. And we call it a solution when it's an equation, like in example 1. So the second example here, g of x is equal to x squared minus 9x plus 27. Oh, that's example B. You'll see when I graph it, this doesn't cross the x-axis, right? Because when I was working out the quadratic formula, notice this, b squared minus 4ac is negative 27. I'm going to scroll up. Right? Back up here, what ended up being the discriminant, right? Right underneath the radical here is a negative 27. That negative 27 underneath the radical gave me an imaginary part, which gave me a complex solution. So look back down here. Because I get a negative discriminant will give me two non-real complex solutions. Non-real being like imaginary, right? Non-real is complex. It's kind of redundant. Two non-real complex. Non-real means complex. I'm taking the language from the assignment to try to make it seamless, so I'm just using their language here. Now my third example, h of x, is not example C from above, because I needed an example of when I have one real solution. Okay, so one real solution is going to be when the graph crosses the x-axis in one point, all right? And that occurs when my discriminant is 0. So 0 discriminant means I have one real solution. And that solution could actually be rational or irrational. I'm going to delete this. You might need to change your notes a little bit. One real root or solution. In this case, it is rational, but it doesn't have to be. So there's a note down here. It says when we talk about functions, our answers are roots. When we talk about equations, our answers are solutions. I kind of explained that up here in this multicolored notes that I made. Just a reminder. Okay, so when I do the discriminant, I am going to look for, I'm going to plug in b squared minus 4ac. And then I want to know whether that is 0, negative, or positive. If it's 0, then I have one real solution. If it's negative, then I have two complex solutions. And if it's positive, then I have two real solutions. And we're going to go one step further here. We are going to determine if they are, this isn't going to really fit, rational or irrational. Okay, so this is kind of my map here. Example 2. Find the discriminant for the following equation, then use it to determine the number of distinct solutions. So I've got some new examples here. Below it, you'll see this A, B, C, D. I took this is just a snipping, it's a picture of the exact wording that comes off of the 5.3 Savas homework. So this is written in standard form already. So I can go ahead and identify A, which is 2, B, which is 6, and C, which is 3, and I'll plug it in. B is 6, so I have 6 squared minus 4 times a, which is 2, times c, which is 3. B squared, 6 squared is 36. 4 times 2 times 3 is 24, and I'm left with 12. 12 is a positive discriminant. So the problem's going to ask for two things. Find the discriminant of the following equation. So the discriminant is 12. That's part of the answer. And then use it to answer the multiple choice question. So this means that I have two real solutions. Okay, because it's a positive number. But now I have to decide whether that's rational or irrational. So it is going to be rational when that number is a perfect square. Like 9, 25, 100. If it's like a perfect square, then it's going to be rational. Otherwise, it's going to be irrational. So I have, my options are the equation has two distinct irrational solutions. The equation has two distinct rational solutions. The equation has one distinct rational solution, so that's not it. The equation has two distinct non-real complex solutions. That's not it, because it's not complex, right? I already decided that I was real because it's positive. Is 12 a perfect square? No. Therefore, these are irrational solutions. So my answer is A. Okay. So for B, please pause this video and go ahead and find the value of the discriminant and take a guess for whether that discriminant gives you solutions that fit under A, B, C, or D. All right? So go ahead, pause, and then come back to find out if you did it correctly. Okay, so you should have already tried this problem. I'm going to go ahead and work it out here. If you did it right, you should have gotten a discriminant of negative 80. So if you got negative 80, good job. All right, negative 2 quantity squared gives me 4. 4 times 3 times 7 gives me 84. 4 minus 84 is negative 80. So that's part of my answer. That's my discriminant. Now, following this little flow chart, is that 0, negative, or positive? Oh, it's negative. That means I have two complex solutions. So which one says complex solution? D. So the answer here is D. Two complex solutions. Okay. And the last one, C. Again, I suggest you pause this and check out, give it a try before you just look at my answer. Before I even start this one, I do have to move the 9 over. All right. So if you did this one correctly, you'll get an answer of 0. Plug in 12 for B, plug in 4 for A, and 9 for C. 12 squared is 144. 4 times 4 times 9 is 144. So 144 minus 144 is 0. That's the value of my discriminant. And then if I look up at my flow chart here, what happens when the discriminant is 0? I have one real solution. So for C, I have one rational real solution. So the answer is C. We didn't see an example for B, but B would look like is this would be like a perfect square integer, right? So if I got like above, like I said, 9 and 25 and 100, if I got, I don't know, like 16, okay, then that would be what would fall under B. Okay, and that are the end of our notes. All right. Thank you so much for tuning in. Have a great day. Bye-bye.